Many of you might have seen this image of a nuclear reactor with blue light filling the entire volume of the water. This blue light is known as the Cherenkov radiation, and this light is produced only when the particle is moving faster than the speed of light in the given medium. Now you may ask, hey, how can something travel faster than light? Then you would be correct. Nothing can travel faster than light in vacuum, but in any other media, any other dielectric media, light travels much slower, and therefore we can have particles which travel faster than the light in the given medium for short periods of time. For a particle to move faster than the speed of light in any media, it needs enormous amount of energy, so it requires some highly energetic processes like nuclear fusion, which is why we can see this in the nuclear reactors and commonly nowhere else. So, what really happens when a charged particle passes through a dielectric medium faster than the speed of light? You may all know that when a charged particle passes through a medium, it polarizes the medium around it. This polarization, though, is usually symmetrical in nature around the particle. But as you all know, since the polarization is also mediated by photons, so when the particle is moving faster than the speed of light, the light particles, photons, cannot reach the molecules in front of the particles. So then we have a situation in which the polarization is not symmetrical, and we have a directional polarization creating a dipole moment. And it is this dipole moment which creates the Cherenkov radiation. So when that happens, the particle emits light in the shape of a cone while losing energy, and eventually the particle loses enough energy that its velocity now drops back below the speed of light and the Cherenkov radiation stops. So in a way, it is very much similar to the sonic boom, which happens when an object is moving faster than the speed of sound in a given medium, which creates a burst of loud thunderous noise. Now, why is this Cherenkov radiation so important for the study of physics and the universe? So, this Cherenkov radiation has a unique signature for each individual particles. These unique signatures are then exploited to identify and study individual particles in various fields of particle physics and astronomy. And to this day, this remains only one of the few ways in which we can study one of the most mysterious particles in the universe, which are the neutrinos. The neutrinos hold key to our understanding of the universe at a very deep level, and one of the experiments which aims to study and to solve these mysteries of the universe is the Super Kamiokande detector in Japan. This detector is located 1000 meters below the Earth's surface so that outside events like cosmic rays do not impact the measurements and the results of the experiment. And it is a huge, when I say huge, it holds 50,000 tons of ultra pure water. It's a huge cylindrical tank of water. So, why do we need this huge volume of water? The goal is to study neutrinos. As I have said earlier, they are very mysterious particles. So, for an example, there are 100 trillion neutrinos passing through your body every second without interacting with you at all. So we need this gigantic volume so that we can get even one or two reactions occasionally. The more volume you have, the more likely it gets that you can actually detect one of these particles. What happens when a neutrino finally passes through and eventually hits one of the particles in the medium. So when a collision occurs with a neutrino with, say, an atom or the electrons around it, it can transfer enough energy to the electron so that it accelerates and travels faster than light for a very short period of time. And you know what happens when a charged particle goes faster than the speed of light? Yes, exactly. It can produce Cherenkov radiation. But as I said previously, the interactions of neutrinos with the matter are very, very minuscule. So most of the time we might have one charged accelerating electron, and we need to detect that single electron moving through the medium. The Cherenkov radiation is usually quite faint, and especially so when it is produced by a single particle. That's why we have 11,200 photomultipliers tube attached to the detector, which can detect even a single photon generated in the medium. So here we have an example of one such event in the T2K neutrino oscillation experiment. So the main idea of this experiment was to find out whether there were more than one kind of neutrinos that exist in this universe. And this is one of the first discoveries and one of the main important discoveries of this experimental setup in the Super Kamiokande detector. From the pattern of the cones and the light distributed in the different regions of the detector, we can see if they were from the same particle or a different type of particle. So this experiment proved that one type of neutrino changes into another one in a phenomenon which is termed as neutrino oscillations. This neutrino oscillation is also a proof that the neutrinos possess mass, which is also very significant since for the time being all we knew about neutrinos were they traveled almost at the speed of light, which is an indication of a very, very light or a massless particle. Now we have discovered that at least two types of these neutrinos have mass, a very, very, very tiny mass, but still non-zero. Now let's have a look at the main experiment which is going on currently, which is the proton decay experiment. The grand unified theory, which unifies the main three fundamental forces of the universe, strong, weak, and electromagnetic interactions, predicts that proton will decay to lighter particles like mesons and leptons. This is in stark contrast with the current theory of model and particle physics, in which proton is considered as a stable particle. As you all know, proton is fundamental particle of all atoms and molecules, which are integral for our survival. So a proton decay will have a huge implication for the theoretical structure of particle physics. So when the proton decays in its most natural or likely form, we can see a neutral pion which decays into two photons, and we can observe three electron-like rings in the Super Kamiokande. So if the proton decays, all materials in the world will be broken in the future into smaller particles like electrons and photons. So how dangerous is this decay for us? From the theory we know it's not that much. From the theory it is predicted that the lifetime of such a decay will be longer than the age of the universe itself. So how can we measure such a long lifetime? That is why we need a large quantities of water so that we will have sufficient protons that even a decay in a long periods of time can be observed. even if the lifetime is so long, the total number of protons will still follow an exponential decay. So if we have enough protons, we can observe the decay of an old proton once in a while. And as we look for the signatures, we can see and measure the actual lifetime of the proton and whether or not it decays at all. So what have you observed so far? The Super Kamiokande has been measuring this since 1996, and it has been more than 20 years into running. However, we have not observed any evidence for the decay of protons. It is a great thing for us, but not so from the theoretical physics standpoint of view. Then we will have to look for new ways to unify the strong interaction with the electroweak interactions. From this result, the proton lifetime is estimated to be longer than 2 times 10 to the power 34 years, which is way bigger than the age of the universe, which is approximately 10 billion years. So, what is the next step? How do we improve the result, and what are we looking for the future? So, the improvement to the Super Kamiokande detector is already under construction. The Hyper Kamiokande detector with even larger dimensions and a much larger amount of water. So we will be more sensitive to any decay and to any neutrinos coming into the system. And the goals of the next Hyper Kamiokande detector includes the discovery of the difference between neutrino and antineutrino oscillations, the further development of neutrino astronomy, and the proof of the unification of elementary particles and the unification of electromagnetic weak and strong force by the discovery of proton decay. We may or may not discover these things, but I think it will still be an exciting few years for the detector. So that is it for this video. If you like the video, please like and subscribe. And if you have any comments or suggestions or criticisms, please leave that below. See you next time, hopefully very soon.